Right now you are seeing kaleidoscopic patterns here, which are repetition of some basic pattern, and today I will introduce and describe fractal patterns and how they occur in nature, how we can compute an important mathematical property of fractal images, and how they are everywhere. So first, let me say that we have all been taught classical geometry, which is Euclidean geometry, and in which we have been introduced to concepts like points, lines, rectangles, spheres, cones. So this piece of paper is a rectangle, so is the book, so is your mobile phone. This line, this pen is a line, and classical geometry works very well with such objects. However, if you were to describe natural objects such as clouds, surfaces of mountains, river networks, then classical geometry is not really sufficient to describe that. How will you describe a cloud in terms of points, lines, spheres? So you need different kind of mathematics for that, which is fractal geometry. Intuitively, a fractal image on an object is self-similar. So if you take a small part of it and magnify, then it should resemble the whole. For example, look at this broccoli here. If you were to take a small piece of broccoli and if you were to magnify that, then it will resemble the entire broccoli. So it's a fractal object. Here are a couple of books on fractals, and at the back cover of this book there are certain fractal images which are displayed. Here is a fractal landscape with a mountain. Suppose you are hired for a Hollywood company to create special effects, and you have to create landscape of an alien planet. Then how will you create such a computer graphical model? It will be very hard for you to describe all the details in terms of classical geometry, but fractals give you more compact models and compact algorithms to generate such landscapes. Here is another book on fractals, and if you were to look at this fern, then it's a fractal object, because if you were to look at piece of fern here, it resembles the entire fern. My daughter is reading this particular book, which is illustrated by P.J. Lynch. Beautiful illustrations in this book. And if you were to look at some of the illustrations here, for example, this is a scene of rural countryside, and if you were to look at this tree and these stones here, they are fractal. If you were to look at branch of a tree, then it will resemble the entire tree. This is another scene. These are stalagmites and stalagmites, and you can see these patterns here which are very fractal like. This is night sky and distribution of stars and galaxies in the universe. They also follow fractal So I will now show how to compute an important mathematical property called fractal dimension. So for example, if you were to look at this classical Sierpinski triangle, it's a self-similar triangle, and what we'll do, we will capture the complexity of this fractal image in terms of a number, and that number is called fractal dimension. So what we have to do here, we have to find how many self-similar copies it has and what's the magnification factor. So we can see here there are 3 self-similar copies. This is the first one, this is the second one, and this is the third one, and magnification factor is 2. So the formula is number of self-similar copies is proportional to magnification factor raised to this exponent d, which is fractal dimension. Or alternatively, you can say that d is log of number of self-similar copies divided by log of magnification factor. And if you were to compute this number for Sierpinski triangle, then there are 3 self-similar copies and magnification factor is 2, and which is approximately 1.58, which is the fractal dimension of Sierpinski triangle. Now let me show you Koch snowflake fractal curve. And if we were to compute fractal dimension using the same technique, then we can take one of the sides here, which would look like this, and here there's a version of the same side hand drawn. So we can take this as a copy, there's another copy, third copy, and fourth copy. So there are 4 copies, and here magnification factor is 3, which is magnification factor. So if you were to zoom any of these pieces here by a factor of 3, then it will resemble the entire Koch snowflake. So here the fractal dimension will be log of 4 divided by log of 3, which will be approximately 1.26, which basically means that this snowflake curve lives in a space which is in between one-dimensional space and two-dimensional space, because though it looks like a line, at the same time it is really undulating here, and it is trying to fill up the two-dimensional space. That's why this number comes out to be between 1 and 2. So in general, fractal objects will have a fractal or fractional dimension. If this becomes almost like a space filling, then it will approach dimension 2, which will be the topological dimension. Now let me give you some examples of applications of fractals. So one was computer graphics, special effects. Then you can model a lot of natural processes, natural phenomena using fractals. For example, if you are modeling biochemical reactions in a cell in biology, then if you were to treat the cytoplasm as a fractal, it gives you more accurate answers. It has application in chaos theory, in which we describe chaotic systems or highly complex systems, and they have strange attractors and which have fractal characteristics. And also you can use them to generate art, beautiful architecture. If we were to relax the mathematical requirement of having a contractive transformation. So coming to this kaleidoscope pattern which you saw in the beginning, so it is a repetition of the same pattern, or so is this piece of fabric here. You have repetition of certain patterns. So you are using same mathematical transformations except that they are not contractive. If I were to create same pattern here at a smaller scale, suppose we had this circular pattern over here in a small scale, then we would have had 2 iterations of fractal generating process. So repetitions sometimes people think are fractal images, but mathematically you need a contraction to occur. At the same time, if you write a software which will generate fractal images, it can also generate these repetitive structures. And in order to describe natural objects, we have to relax these mathematical requirements, because in mathematics we idealize certain concepts, we take things to infinity, but in practice we will have multifractals or superfractals or hierarchical factors, because things are made of different components, each will have different model. So we need to relax these requirements in order to generate these beautiful images. I think that will conclude my lecture here. Next time when you encounter a broccoli or you see a cloud, I'm sure that you will see fractals there. Thank you.